Hello, everybody. As folks start to trickle in, it is wonderful to see you on this Monday morning. We'll get started here in just about a minute. Give everybody time to join. Alrighty, hello everyone, and welcome to the Environmental Law Institute's webinar, Understanding Hydrogen, the Colors, Production Processes, and Opportunities for Decarbonization. My name is Sarah Viken, and I'm the Manager of Educational Programs here at ELI. We have an amazing program lined up for you today. With increased investment and attention going towards hydrogen's role in decarbonizing the energy grid, we decided to hold a program to explore its different production methods and look to the future. I want to thank all of our wonderful speakers for being here today and for taking the time to prepare insightful content for this program. I also want to thank our audience for tuning in. We always appreciate your interest in all of our topics, but especially this one. Today's program will feature commentaries from our 4 wonderful panelists, as well as our moderator, and a roundtable discussion. While we will be taking questions further along in the program, please don't wait to submit them. You can use Zoom's Q&A function at any time throughout the webinar, so please don't wait, and our moderator and speakers will be able to see it. We encourage you to use the chat as well for any observations or comments, but just be aware that we'll be pulling discussion questions from that Q&A box and not from the chat. Today's webinar will be posted and recorded and posted on the event webpage for ELI members to view later. So if you are an ELI member and you're not able to stay for the entire 90 minutes today, the recording will be available within a few business days. You can find the recording as well as more information on becoming a member at eli.org. Now, before we get started, I want to introduce our wonderful speakers. Starting us off will be Shailesh Sahai, your moderator for today. Shailesh is a partner at the Environmental Safety and Incident Response Practice at Baker Botts. He previously served as in-house counsel to the largest renewable fuels producer in the world and as acting general counsel of the largest renewable fuels trade association. He directs legal and policy strategy on climate, environmental, and sustainability issues at the federal, state, and international levels. Thanks so much for joining us, Shay. Now, our first speaker will be Beth Dean, Chief Legal Officer at Electric Hydrogen, a manufacturer of PEM electrolyzer plants used to produce green hydrogen. Prior to joining Electric Hydrogen, Beth was Vice President and Deputy General Counsel at Leeward Renewable Energy, a U.S. energy company with wind and solar facilities and operation across 9 states. Now, before joining Leeward, Beth was Chief Counsel of Project Development at First Solar, a global manufacturer of solar panels. In these roles, she's been involved in all aspects of renewable energy manufacturing, development, and operation, as well as having responsibility for a wide variety of transactional, litigation, regulatory, and corporate matters. Thanks so much for joining us, Beth. Following Beth will be Rick Butel, Vice President of Bloom Energy's hydrogen business. Rick spearheads the company's market strategy and serves as an evangelist for emerging hydrogen solutions. Rick brings over 3 decades of experience in the energy and industrial sectors, including deploying and scaling hydrogen projects across international markets. Before joining Bloom, Rick served as Vice President of Business Development at Air Products, where he oversaw the development and execution of countless large-scale energy projects. During this time, he was responsible for the deployment of over $10 billion of capital, including world-scale clean hydrogen, renewable fuels, and ammonia projects, and other projects centered around gray, blue, and green hydrogen and synthesis gas production. Thanks so much, Rick. Next, we'll have Alina Templinsky, a partner and the energy industry group leader at Pillsbury Winthrop Shaw Pittman, where she co-leads the firm's hydrogen practice. Here she works on energy transition projects, policy, and regulation, with a particular focus on hydrogen and nuclear energy. Alina is a trusted advisor to owner-operators, equipment suppliers, investors, architect engineering companies, and technical consulting firms on complex energy, transactional, and regulatory matters. She frequently serves as lead counsel on new build projects, equipment and fuel procurements, M&A transactions, and joint ventures in the nuclear sector. She is also serving as counsel on a number of hydrogen transactions, including advising on hydrogen hubs recently selected by the DOE. Alina has worked on energy projects in more than 30 countries and is co-leading the Nuclear Hydrogen Initiative. She also advises energy and technology companies on the commercialization of innovative zero-carbon technologies, including hydrogen production, storage, and transportation facilities, advanced nuclear reactors, and zero-carbon fuels. Thanks for being here, Alina. And finally, we'll hear from Pete Budden, who leads the Natural Resource Defense Council's state and regional level hydrogen policy work. Prior to joining NRDC, Budden researched the next generation of solar energy technology, earning his PhD in physics and undertaking a postdoctoral fellowship. He also worked for the Climate Change Committee in the UK as an industrial decarbonization analyst, where he modeled decarbonization pathways for the UK industrial sector, assessing the emissions reductions potential of competing technologies, including hydrogen. His work informed the UK's 2030 NDC and sixth carbon budget targets. Pete graduated from the University of Cambridge and the University of Oxford and is now based at NRDC's office in New York. A big thank you to all of our speakers for their time today. And with that, I'll turn it over to Shay to get started.
Thanks so much, Sarah. Really looking forward to the conversation today. So by its nature, hydrogen is a very complicated topic, which is a little bit ironic because it's one of the simplest molecules, two hydrogen atoms bonded together. But there's a lot going on in the field. And so what I wanted to do was just start with a little bit of kind of a diverse, disparate set of issues that people often think about when they think about hydrogen. So I'm going to walk through a bunch of them. They might seem disconnected at this point, but I think you'll find some of these topics emerge as we continue the conversation today with our fantastic panel. So first, I just wanted to describe what the current applications of hydrogen are. It's important to understand kind of what it's currently being used for, and then potentially where the market is headed in the future. So currently, these are what hydrogen is used for: refining, ammonia, methanol, metal processing, and then some boutique usages. And I think in the future, we're going to see both new applications. Obviously, transportation use of hydrogen in particular is one of the big ones. EPA wants hydrogen to be used to directly power plants. That's a big part of the new Clean Power Plan. So you'll see some new applications that are not listed on this current slide emerging in the future. But then you also see, I think, transformation within these sectors. For example, within the refining sphere, you'll see that even a current use of hydrogen is the refining of biomass and biogas, with kind of decarbonization incentives probably increasing into the future. I think you'll see that bucket of refining grow. Methanol is another area where you can create methanol from recycled or captured CO2. So you could see kind of that bucket grow consistent with decarbonization goals. And then things like going back to the refining area, using hydrogen to make sustainable aviation fuel. So in a sense, you'll see these existing applications will morph into new things as the energy market changes, and we'll see some new applications as well. So where does this hydrogen come from? Currently, really three technologies really dominate the hydrogen market. The largest by far is steam methane reformation of natural gas, which is essentially just combining natural gas and methane at high temperatures in the presence of a catalyst. And that again produces hydrogen and carbon monoxide. So that's the by far the largest source of hydrogen, both in the United States and worldwide. There's also coal gasification, which is just heating up coal in the absence of oxygen. There you get syngas, which is methane, CO, and hydrogen, more or less. And then electrolysis, which is just splitting up a water molecule with electricity. Obviously, you get hydrogen and oxygen then. So those are the three primary ways it's produced, with SMR being the dominant way to produce it, and coal playing a larger role on the world stage. So very quickly, here's an introduction to the different colors of hydrogen we're going to walk through on the call today. Coal gasification is often characterized as black or brown hydrogen. Gray hydrogen generally refers to hydrogen derived from natural gas without the use of carbon capture. Green hydrogen is electrolysis-based hydrogen where you use renewable energy like wind or solar as electricity source. Blue is hydrogen produced from natural gas where you then capture the carbon and sequester it or potentially use it in another product. Methane pyrolysis is kind of similar to coal gasification. Here you heat the methane in the absence of oxygen, but the kind of reaction parameters are different. And my understanding is that you end up with, or you can end up with hydrogen and a solid form of carbon as a result of this pyrolysis pathway. Rick will get into that in some more detail during his presentation. And then pink hydrogen is electrolysis based hydrogen using nuclear power as the electricity source. And then white hydrogen, which I thought was kind of a throwaway category, is another interesting source. That's naturally occurring hydrogen. I was just scrolling through CNN this morning, and they apparently found some relatively large deposit of white hydrogen in France. And I guess there have been some deposits discovered in Africa as well. So it would seem difficult to me from a gut sense to find hydrogen naturally occurring in rocks because it's so reactive, but apparently they're finding it. And so who knows, this might be a significant source of hydrogen moving forward. So one significant issue to think about, and I'm sure some of the panelists will touch on this, is how to transport hydrogen once it's created. So as I mentioned, EPA and the new version of the Clean Power Plan is proposing more hydrogen use at natural gas fired power plants. One way to do that is just to insert hydrogen into natural gas pipelines. A lot of folks who are familiar with pipeline kind of mechanics and physics, though, are concerned that this is going to create some safety issues with pipelines, and that current current natural gas pipelines aren't particularly well suited to carry significant amounts of hydrogen. But that's something that folks are experimenting with. Of course, you can just liquefy the hydrogen and transport it that way. Obviously, liquefaction takes a significant amount of energy, and hydrogen is quite reactive. So there's some limitations potentially to that mode of transporting hydrogen. And then another option is to take the hydrogen and convert it into a different molecule for transportation purposes. Ammonia and methanol have both been proposed essentially as hydrogen carriers. Of course, it takes energy to go from hydrogen to ammonia and then energy to go from ammonia back to hydrogen. So there are some costs with those processes as well. But I think all of these are on the table in one way or another, depending on the application for hydrogen transport. Another issue to think about is, obviously we're going to use this hydrogen domestically, but we're also going to end up exporting it to Europe. And in Europe, the RED II regulations are pretty specific as to what types of hydrogens qualify as renewable fuel of non-biological origin, which is the fuel category that qualifies for certain incentives and requirements under the RED II program in Europe. So under RED II, 100% of the energy used to produce the hydrogen has to be from renewable energy, and you have to have a CI reduction of 70% compared to fossil fuel equivalents. So that's pretty significant. Alina can talk to this more, but I think that's posing, some challenges in the short run, at least, with respect to pink hydrogen. And we'll see kind of how the EU deals with those requirements moving forward. It gets a little bit more complicated as laid out in this slide, but I'll leave it there for now. Yet another significant issue is water use when creating hydrogen. Obviously, steam methane reforming, since it uses steam, requires a lot of water. Hydrolysis uses water as the feedstock. So a major question we're going to face into the future as hydrogen becomes a more significant part of the fuel supply is where we're going to get the water that's required for these various technological processes. A hot topic from the Inflation Reduction Act is the 45V tax credit. So this was a tax credit designed specifically to reward the production of hydrogen in the United States. And the way the credit works is that the amount of the credit scales up with the amount of CI reduction compared to fossil-based hydrogen. So fossil-based hydrogen has, I think, a CI of about 10 to 15, typically, kilograms of CO2e per kilogram of hydrogen. And here you can see there's scaling incentives based on how low you can get the CI of these alternative sources of hydrogen to go. The kind of technologies that show promise for the kind of most significant CI reductions are green hydrogen and pink hydrogen, likely. Blue hydrogen can have significant reductions, but I think a lot of folks feel like it's going to be challenging for blue hydrogen to meet the most stringent category. There are folks who can explain who think that blue hydrogen will qualify for this, or can qualify for this kind of second tier $1 tax credit. And I just saw a question flash up on the screen as to kind of what CI is. So CI is the carbon intensity of a product, and so that's typically the amount of CO2 that's generated per metric associated with that product. So when you're talking about hydrogen, you're talking about CO2 per kilogram of hydrogen produced. When you're talking about kind of fuels more generally, you often talk about kilograms of CO2 per unit of energy in the fuels, so you can standardize across various fuels. A major issue that's going to be, or a couple of issues that we're going to encounter with the 45V tax credit, which I think other folks will hit on more later in the conversation, are the choice of model. Currently, the IRA points to the Argonne GREET model, which is a way to kind of figure out what the CI of hydrogen will be. And then this idea of additionality, which is essentially that we want renewable energy that's being used for hydrogen production to be essentially a new or additional form of renewable energy. So the idea is that you don't want wind energy to be used for hydrogen production only for that wind energy to be replaced on the grid, for example, with coal production, right? And so this idea of additionality, a lot of people think is important when thinking about where the energy is going that's going to be used for hydrogen production. Kind of breeze through this. I guess the last topic I wanted to hit, just as a general matter, was the topic of hydrogen hubs. The bipartisan infrastructure law, so the big package that had been passed prior to the IRA, had set aside $7 billion for regional hydrogen hubs. And so the DOE just last week awarded 7 grants of approximately $1 billion each to regional hydrogen hubs. They still need to go through a lot before they get the money, but this money is the purpose is to build out hydrogen infrastructure in these areas. So to help projects producing hydrogen, to help develop hydrogen pipelines, to help develop the economy around folks using hydrogen. So that money has been tentatively allocated, and it'll be pretty exciting to see how each of these hubs develops moving into the future. All right, well, that's all I had in terms of just a variety of introductory topics, but I'm really excited to get into the rest of the presentation. So Beth, I think you're up first.
Yeah, thanks, Shay.
Right,
Really great overview. Thank you. So what I want to talk about is green hydrogen. That is what electric hydrogen was really established to make or help make through our technology. And I'm going to cover some of the same things that Shay covered, but hopefully in a little more detail around green hydrogen. So, why is green hydrogen suddenly now a thing? Like it's hydrogen has been around a long time. Electrolysis has been around a long time. But what's making it possible to think about green hydrogen as a clean source of a clean molecule, if you will? And that is really that it's just due to the fact that renewables have come down in price significantly. I come from a solar background, and we started out with solar being a very expensive resource, and it's through the advent of technology improvements and the scaling of the technology, we've really been able to bring that way down, so that it's really the fastest growing source of energy in the world, wind and solar, and hydro. So the IEA estimates that by 2027, which is not very far away, renewables are going to be about 38% of our energy source. So that is a huge evolution. And so it's sort of the natural thing is, what can you do to use that renewable energy? Can you electrify everything? Probably not. I mean, there are certain industries where you really do need the heat, or the intensity of the production process requires that there be a molecule rather than an electron. And there's sort of limitations around moving electrons around. You need wires. And sometimes you are going to want to move the energy across, or globally across continents and so on. So what is sort of envisioned now, sort of globally, but obviously very, very much focused here in the US as well, is that hydrogen can step up and provide this sort of what has been a missing link, to provide a clean fuel, if you will. So how is that going to sort of evolve, and what is sort of the relative sort of places to play? I think that what people really see hydrogen doing is working in these industries that are listed here on this slide below. Some of the same things that Shay mentioned: chemicals, refining, anywhere where you need industrial heat, steel. I think there is a vision where hydrogen could be used to firm up electricity, so be able to produce hydrogen, store it, and then bring it out when needed. Or, as I said, to kind of ship it, between continents. I think there's other kinds of fuel uses, and then there's also uses for maritime and also for aviation. I think clean hydrogen is something that there is a lot of potential for. And when you think about it, 30% of our emissions are coming from these, sort of what are called hard to decarbonize industries. And they're using a lot of our power, up to 38%. So this place to focus is going to have a significant impact if we can figure out how to deliver green hydrogen in a cost-effective way. And just to recap, this is just sort of where the markets are, a little bit of sort of overview of what Shay was saying in terms of the places and the kind of normal everyday names you sort of associate with these industries. If we're really going to turn use of fossil fuel into use of green hydrogen, we're going to need thousands of gigawatts of green hydrogen, and other kinds of hydrogen. So this is just to give you kind of a sense of the scale that we're talking about, and the kind of places that we're going to need to look. And again, just to kind of recap, we're not, green hydrogen is not going to produce replace electrical clean energy. It's just a supplement. It's really, we're going to go down the green path on the bottom here. There may be places where there's some overlap, but for the most part, fueling our cars and our houses, that's going to remain, a renewable energy, wind, solar, hydro, nuclear kind of solution. But when it really comes to some of these other industries, this creates a huge opportunity. So I'm not sure why that skipped ahead. For some reason, I'm not seeing the controls anymore. And it's making my slides, I'm just hitting, there we go, suddenly appeared. Sorry about that. just to sort of recap on sort of what our goals are, just to bring it from the sort of international possibility, 3 terawatts of potential down into the US. These are just the administration's, our own government sort of goals right now, which is 50% reduction in greenhouse gas emissions by 2030, ambitious. 100% carbon-free electricity by 2035. Right now, we're very far away from that, and I'll talk a little bit more about that. And then net zero greenhouse gas emissions by 2050, which is a lot of what we're lining up for, and the rest of the world is also lining up for. So that is sort of the context of all of this discussion, is sort of how do you meet these goals? And really, I wanted to lay out where DOE is sort of seeing hydrogen play within those broader goals. And that's really right now where the US produces in the range of 10 to 12 metric tons of hydrogen each year. So DOE is really envisioning that hydrogen become clean by 2030, essentially, and then to continue to build on that through 2040 and 2050. And their goal is that would, really see a significant reduction in greenhouse gas across the whole economy, and result actually in a lot more jobs to build up this new clean hydrogen industry. And so, kind of to think about a little bit about how that's going to happen. DOE has laid out their hydrogen goals in a roadmap. It's a great document, it's available on their website. And this is just a screenshot of, sort of what they are thinking about. So the first strategy is what I've already talked about in terms of decarbonizing those industries. And, the second strategy is really to bring the cost down. And that is, that's what's going to make the difference, because if just like, renewables are now cheaper in a lot of cases than fossil fuels, if green hydrogen is cheaper than fossil fuels, people will use green hydrogen. It's that simple, really. So, what the target, the DOE, and just pulling this out from their work here, is shooting for is, $1 per kilogram for the cost of clean hydrogen by 2031. And, right now, fossil fuel hydrogen ranges from $1 to $3, depending on how it's produced and so on. So that gives you sort of the sort of where DOE is headed and why they're picking that number. And so I really want to talk about like how electric hydrogen fits within that, because I think that's part of like what we're doing is relevant to the rest of the industry. We really looked at this and said, what does the world need right now? It needs, much larger scale, because these industries are big industries, and because, to really address the market, you need to like think much bigger. So we are have innovated a product that is, first of all, on a scale that is much larger than what's currently available, and it's a much lower cost plant. We've innovated on our technology to really produce more hydrogen with fewer electrolyzer stacks, which is the part that actually separates the water in an electrolysis plant, to bring down the cost and really optimize. And then we're really delivering the entire plant pre-assembled. So we put the picture of this plant, we put this all onto skids, which then ship out on the back of a truck to the customer site. So what that means is we can just bring down the cost significantly. We've already seen a huge cost reduction. We're going into production with this. Our factory will be done towards the end of this year, and we'll be building our first plant next year. So we're moving very quickly with the goal to just bring down the cost of hydrogen right along in the same direction and along the same time frame that DOE is asking, because we really see that as the path to getting at this industrial emission source that has been hard and difficult to make a change in. And then we're also, designing our system to be able to follow the load that is generated by, follow the load and then the resource that's generated by wind and solar, which means that you have to be able to ramp up and down to follow when the sun is shining, when the wind is blowing. So that's a key component of our technology. So again, we're just one company, but we're out there trying to like follow this evolution in a way that really makes a difference in terms of cost. And so, I want to talk a little bit about, since this is the Environmental Law Institute, I want to talk a little bit about the laws that are sort of driving, I think, what will be a significant evolution. In the same way that renewables were an evolution, hydrogen is at that pivot point. The Inflation Reduction Act created a significant opportunity for all colors of hydrogen. And this is the same chart that Shay showed. I put it up just to kind of give a transition. All statutes require implementing regulations, and that's the stage at which we are right now. The statute was adopted last year in August, and the Treasury Department, along with advice from the Department of Energy, have been working on all sorts of implementing regulations for all pieces of a much bigger bill for the whole Inflation Reduction Act. But they're currently working on the implementing regulations and guidance that are going to be coming out for 45V. So that's the stage we're at right now. And, you know, there are lots of issues because how you do things always matters. It's not just the sort of the broad statutory directive, but then, you know, how it's actually going to be implemented raises all sorts of questions. And particularly for 45V, when you're talking about really creating an opportunity to kind of guide how emissions are tracked and make, you know, you get the credit because you're bringing down emissions, basically, is the whole idea of the statute. You need to think about like how you're tracking and accounting for those emissions so it's fair, and so you actually end up with less greenhouse gases at the end of the day. So for blue hydrogen, some of the things that the Treasury Department is grappling with is leakage from pipelines, for example, and you know, how you measure that leakage. Is it real out in the field measurement? Is it some sort of approximation? Those things matter. For green hydrogen, it's use of grid energy, and I'll talk a little bit more about that as I finish up here. For carbon sequestration, it's, you know, sort of the integrity of the long-term storage and its reliability. Also, like if you're capturing carbon, do you get to use it for something else? Can you get another incentive, a fuel incentive, and a you know, IRA incentive? Probably not, right? So you're going to want to like think about like the different ways this actually works in the real world. There can be some unintended impacts in terms of like if you encourage use of the grid in different ways under these requirements, it can have impacts on congestion on the grid, or it can have impacts on electricity prices. So those are just some of the questions that the Treasury Department is being asked to sort of think about and work on. I think what's important is on all sides of all of these debates is, you know, we're all trying to get to clean hydrogen fast, accuracy, and then the long-term integrity of the credit. Those are the drivers of a lot of discussion around these implementing regulations. So I'm going to focus on green again in terms of the implementing piece. So first of all, why $3? You know, where did that come from? It's pretty simple, really. The current cost of making green hydrogen is somewhere in the range of $4 to $6 as estimated. These are all DOE kinds of numbers, and other consultants tend to back them up. The cost of gray is somewhere in the range of $1 to $3. So the $3, you know, gets this interim parity going. And the idea is the incentive helps for some period of time until the industry can bring down the cost naturally, just like it happened, you know, the curve on renewables. The same thing can happen with electrolysis. And so the idea is sort of an interim incentive with using taxpayer monies to really get the industry going, right? And then the big question for green hydrogen is, can you use grid energy? It's not always so easy to locate a solar or wind plant right beside where you want to make hydrogen. So it's sort of logical that you'd be able to like maybe use energy from the grid to make the hydrogen, but then, you know, think about the production of renewables somewhere else to offset that. That is a good concept, and I think it's really important to allow the growth of the industry. However, it turns out like the rules you make around that use of the credits or the certificates, sometimes called renewable energy certificates or RECs, how you use those RECs and account for them really makes a difference on whether you're having an impact on emissions or not. It can have some other impacts because if you think about it, if you're putting those two things together in the same place, it sort of is easy to imagine that's low emissions, renewables and hydrogen production. Once you start to separate those things, the grid is actually pretty dirty still. It's still mostly made with fossil fuel. So then you start to have a separation between reality of what's being made and what's not. If you want to drive people to build projects where there's more renewables, you have to have rules that force that behavior and force that kind of innovation to make that work. And so that's really is what it is at the heart of using grid energy and the implementing regulations, is how do you create an accounting system that sort of tracks to that sort of reality. And the way that Europe has really addressed this is through what is commonly called the 3 pillars. Shay alluded to this. It's really trying to look at, like, okay, if you're gonna make hydrogen, do it in the same region, so that you're, again, driving those projects to get built near where there is renewable energy resource, just like you wouldn't go drill for oil where there was no oil. And then if you track to the actual time, then you really will be operating your electrolyzer, your hydrogen production facility to track to when there are renewables. And so these rules around accounting have been applied in Europe. Also additionality, like having a new resource come online so that you're not, the idea is you're not like displacing something else and there's no net gain. All these rules came into being for these reasons, and Europe has adopted this, and they're going through a process to implement this in each country. Probably makes sense for the US as well. And so the phasing that Europe came up with was 2030 for hourly matching. Geographic goes in right away. Additionality 2028. Again, probably in that range. Maybe US can be a little bit faster. We don't have the same regulatory obstacles, but that's the general idea. And then, we're really, by doing that, if we align with where Europe is going, essentially maybe a little faster, we can ensure that there's global standards that are consistent. And then also, like, that really encourages market development and opportunities for US energy developers, US manufacturers, the whole thing. And then, I think one of the things that is interesting is that, I talked a little bit about how electric hydrogen is driving towards a system that can follow the variability. That's innovation, right? If you require this kind of location, you will require that kind of innovation. So, we want to be held to that standard, but we want to make sure that, like, the whole green hydrogen infrastructure is really moving in that direction. So when this credit goes away in 10 years, the industry is actually there and ready to actually optimize renewable resources in a way that is true cost parity. That's the drive, and I think the integrity of the whole thing. And we also want to avoid, using these resources in a way that undermines how the grid already works. If you put making green hydrogen takes a lot of energy, so you can have a huge impact on the grid, and that's sort of unintended. So all of those things, I think, argue in favor of lining up with the 3 pillars. I think a lot of other folks are going to be able to speak to this as well from the other color standpoint, but that's a very high level, quick overview. So thank you, everyone.
Thank you, Beth. And I see, a lot of questions have already started to come in through the Q&A, but I think I'll hold them until we kind of get through all the affirmative presentations. But it was great to get an overview of the green piece of things. Rick, do you want to, both walk us through some of these other colors like blue and turquoise, and then tell us a little bit about your business at Bloom?
Sure, happy to. And thanks to everyone. It's a privilege to be here today talking to the ELI community. So I'm Rick Butel. I look after the hydrogen business at Bloom. As Beth's business, Electric Hydrogen is an electrolyzer company. So is Bloom. Our technology is a bit different. It's based upon a solid oxide-based technology for which Bloom have built and deployed over 1 gigawatt globally. But I think I'm here today to talk to you not so much about that, even though I did sort of see the light and leave the world of gray hydrogen and blue hydrogen at Air Products to cross the Rubicon to green hydrogen now. I'm going to talk to you a little bit more some things that are in my background. So that would be gray hydrogen. As Shay talked about, the principal technology there is steam methane reforming. So we'll talk about that first. I'm then going to talk about blue hydrogen, which is similar but not the same, and then conclude with turquoise. And then I think I'll hand the controls back to Shay, and he can hand over to the next victim. So gray hydrogen, as was covered in the introduction, the overwhelming majority of hydrogen produced in the United States as well as globally today is produced gray. And what that means is that methane, natural gas, and water in the form of steam are reacted at very, very high temperatures in a tube full of catalysts at an elevated temperature to produce synthesis gas. And basically the hydrogen and the CH4 and convert into synthesis gas. The synthesis gas, which is pretty heavily weighted on hydrogen, because if you think about H2O and you think about CH4, there's lots of H's in what's going into that process, right? So what comes out of the back of the process, just keeping this simple, is a mixture of about 70% hydrogen, and then you'd say sort of 30% other cats and dogs. And before you want to purify that into pure hydrogen, you'll actually go through a process called shift, where you'll react some carbon monoxide that's carried over along with some trace amounts of H2O that's carried over in a process called shift. And basically that converts CO plus H2O into CO2 and hydrogen. And then you have a technology called PSA, or pressure swing absorption, that purifies that elevated concentration of hydrogen into pure hydrogen. And then basically the effluent material that's rejected, or what's called in the industry the tail gas, is sent back and used in burners as a fuel, along with air, which comes from the outside world, to heat up this reaction and keep it going. Now, one difference with gray hydrogen versus blue hydrogen that I'll speak about in a few moments is that the carbon dioxide associated with this process appears in two places. So it appears in the form of a flue gas, as that fuel is burned in ambient air. That flue gas is vented, and it has a very, very low CO2 concentration, much like the effluent from a natural gas power plant in the single digits. There's also, as I mentioned, some carbon dioxide in that synthesis gas, which is then rejected and sent back. And that is recoverable. So we'll talk about that in a moment. But why gray hydrogen? Why steam methane reforming? What I would say is, having spent a long time in this industry, up until probably 2018, every conversation I had with a refiner, an ammonia producer, somebody who wanted to use hydrogen literally for rocket fuel, somebody who was using it in metals processing for heat treatment, nobody really cared about the carbon intensity of hydrogen. What did everybody want? They wanted hydrogen that was cheap, and they wanted hydrogen that was reliable. And what mankind has centered upon, especially in parts of the world which are blessed with abundant natural gas, is steam methane reforming as the workhorse technology. If you're a large refiner in the Gulf Coast and you're buying hydrogen today from one of the three industrial gas companies, Air Liquide, Air Products, or Linde, you're paying probably $1 a kilogram based on natural gas being $3 an MMBTU. If you're buying hydrogen in Southern California at a fueling station and you're putting it into your Mirai to drive to wherever it is you want to drive to, and why I raise this is this shows the difference between what it costs to produce on a large volume basis and what it might cost to an ultimate consumer. I mean, today you read a lot of articles that in Southern California, gray hydrogen dispensed at a fueling station is $30 a kilogram. So why is that? Well, in some cases, we don't have enough production of the gray hydrogen close to where some of these use points are. In some cases, It costs an awful lot in terms of supply chain and logistics to get it from the producing plant to a dispensing location, particularly on a really, really small volume basis, like single-digit kilograms, like a fueling station. And in some cases, you would say today, there's just not a lot of competition in terms of the supply of hydrogen for opportunities like this. So one of the really, really interesting things about this is this revolution in clean hydrogen is creating a lot more competition, which is going to help, whether through volume or just simple market forces of supply and demand, create cost pressure and drive the ultimate price down, which will improve adoption. Now, I mentioned gray hydrogen, hence the name. For every ton of hydrogen that's produced for a beneficial use, mankind has been using the atmosphere as a garbage can for the last 100 years or so. And for every ton of hydrogen, you vent about 10 tons per day of carbon dioxide. Until very recently, no one really cared a whole lot about that because, again, the two mantras were cheap and reliable. And this technology absolutely meets that. A lot of people talk about a green premium. I prefer to think about it actually as a gray discount. And you can get this gray discount because today there's no societal or economic penalty for this 10 tons per day of CO2 that's vented for every ton of hydrogen. I think that's something that we'd all acknowledge needs to be addressed long term. Again, lots of H's in the feedstock, CH4 and H2O. So the highest concentration of hydrogen in the syngas relative to other reforming-based technologies. And then people always ask, is it possible to put carbon capture and sequestration on the back of a steam methane reformer and sort of convert it from gray to blue? And what I would say is economically, you can recover about 60% of the carbon dioxide which flows through a steam methane reformer. And that is the carbon dioxide that is entrained in the piping, right, that is associated with the process. So it flows through, it's in the syngas. You can recover it in between shift and PSA and get about 60% of the CO2. The 40% of the CO2 associated with the flue gas, it's just such at a very low percentage, single digits, that it's sort of like recovering carbon dioxide from the flue of a natural gas-fired power plant. It's at such low a percentage, it's not economical to recover. So I would postulate that you can convert gray, and I'm not trying to create a new color, but you can make what we said at Air Products, light blue hydrogen by putting CCS on the back of an SMR. Of course, if you're in a location which is proximate to sequestration, in other words, the long-term storage underground, or enhanced oil recovery, right? It does you no good to capture this CO2 if you can't either get a tax credit for enhanced oil recovery or the higher $85 per ton tax credit for sequestration. So that's gray. You know, I would say my hands are sort of metaphorically dirty. I've sold a lot of gray hydrogen in my lifetime, been around building a lot of SMRs, but up until relatively recently, this was the state of the art. And as Beth talked about, and as Shay talked about as well, this is the lowest cost method of producing hydrogen, excluding the carbon impact of, 10 tons of CO2 per ton of hydrogen. Okay, blue hydrogen. And here I'm going to talk about, I mentioned sort of light blue hydrogen metaphorically on the last slide. Here I'll talk about what the industry considers to be sort of true blue hydrogen. And this is a technology referred to as autothermal reforming, or ATR, although there is a sister and very similar technology called partial oxidation. And depending upon what you're doing with the hydrogen, who the engineering, procurement, and construction contractor is that might be looking to build the plant, who the owner is, et cetera. The choice seems to be predominantly ATR, but economically, there are some circumstances where the concentration of the synthesis gas coming out of the back of the ATR would favor POX instead of ATR. So this is a higher cost technology. Let's start with that than gray. Why is that? Because you see the inputs are, of course, a methane feedstock, a little bit of steam, so consistent with SMR, but another input is actually pure oxygen. So a new process step is required in developing these projects, which means you need to build a pure oxygen generating facility, right? Which is a large air separation plant. And that has two components of cost. It has CapEx, of course, and return on that CapEx, as well as the operating cost. And the principal operating cost for an oxygen generating plant is electricity. Governments of the world have not figured out yet how to tax the air. So let's just think about the parasitic demand here being CapEx and OpEx associated with the ASU. The second reason it's a higher cost is if you look at the inputs, are CH4, O2, and a little bit of steam. There's generally less H's going in per unit of output. So where that manifests itself is you have less H's coming out. And the ratio of hydrogen to carbonates, so CO or CO2, is a bit lower in an ATR or a POX than it is in an SMR. So what that means, if you want to make a given volume of hydrogen for whatever it is you're doing with it, you know, making ammonia, making renewable diesel or methanol or whatever, your POX or ATR process needs to be a little bit larger. Why does this exist? Why does this technology exist if SMR is so much cheaper? Well, what I would say, it's very interesting because the syngas composition coming out of the back of the ATR actually lends itself beautifully today to the production of methanol. And you would say sort of the production of gray methanol, which is a current technology. So that hydrogen to CO ratio is sort of like 1.8 to 1 coming out of the back of an ATR. That's exactly what you need, is sort of methanol grade syngas. And I guess I should have apologized for all the science and all the chemistry coming into this because, like, you know, I roll my eyes a lot too and reminisce back on high school chemistry. So finally, so what's the point? Why am I talking about ATR and why am I talking about blue hydrogen? Well, all of the carbon dioxide is contained in the process piping. So economically, you can recover 95 to 97% of the CO2 and qualify for some of this 45V tax credit. The degree of recovery, the degree of leakage of the natural gas coming to the ATR, the POX will have an influence on that. And there are some technical sort of tricks that you can do to supercharge and improve this. I worked on a project at Air Products in Edmonton, Alberta, where we take a very, very small amount of the product hydrogen and we burn it in a turbine and we make power and we power the whole site and actually oversize it and export some of that power. So, you know, by mathematics, you can call that net zero blue hydrogen. So it is comparable with green. So what I think I would say is that, you know, this is another tool in the toolkit. And if you are looking to make very, very low carbon or zero carbon hydrogen in an area with abundant natural gas and well understood sequestration geology, like the US Gulf Coast, this is a technology to consider. And then finally, I'll spend a minute on another color, so-called turquoise hydrogen. And I think I tried to make the word turquoise here, but it looked better on my screen before I sent it over than it looks here. So the idea here is basically take methane, which is CH4, heat it up to very, very, very high temperatures. And like a lot of these separation processes, the higher temperature you go, the more efficient they become. But in the case of turquoise hydrogen, you run this process at about 900 degrees C. You pass it over a catalyst. And basically, there's two steps of this process. There is a cracking step where the CH4 literally separates into pure carbon and into hydrogen. And then there is a recovery step where the carbon is collected and used as a product. The economics of this process appear to be very, very promising, especially if there is good value for a pure carbon stream coming out of this as a byproduct. In some cases, people are looking at doing this where hydrogen's the byproduct. In some cases, people are looking at doing this where the carbon is the byproduct. And depending on mathematically how you allocate value between these two products, you can make this work. but it is still relatively new. It's been done at a lab scale. It's been done at larger than lab scale. And some of the very, very first projects are under construction today and will be on stream in 2025, 2026. So I think I wanted to leave you with an overview of gray, blue, and turquoise. And with that, Shay, I'll turn the microphone and the controls back to you, my friend.
Sounds good. Thanks, Rick, and thanks for covering all those technologies with your background. That was really helpful. And as a reminder, Rick is now doing green hydrogen and no longer actively working on these other technologies. I think that's what Bloom does. So great. Well, thanks again. We've covered a lot of colors. I think pink is next on the agenda. So Alina, as the nuclear expert, I'll flip it over to you.
Great. Thanks so much, Shane. Pleasure to be with you today. I could certainly talk about all the different colors or greenhouse gas emissions, but as Shay stated, I have a unique expertise in nuclear and the combination of nuclear and hydrogen. So I thought to focus the presentation a bit on nuclear today. So you already heard from Beth about the immense amount of hydrogen that's needed to decarbonize all the hard-to-abate sectors. This is just one projection from McKinsey. I think the one that Beth presented is actually even greater than this. But the bottom line is that we need a significant amounts of hydrogen to be produced via one of these zero carbon or low carbon processes, when today 99% of hydrogen being produced in the world is produced with unabated fossil fuels. And of course, even with just electrification, we're still struggling, as Beth mentioned, to really get even our grid decarbonized, both in the US, but also many other jurisdictions like Europe. So where does nuclear energy come in? Nuclear is actually fairly uniquely positioned to be able to produce hydrogen because it can do that with different types of processes. So today, if we look at what the spectrum of nuclear energy looks in the world, we have about 400 gigawatts of operating nuclear in more than 30 countries. And there are all these existing reactors. There are large light water reactors. It's a technology that's been operating for more than 50 years, very well proven technology. There's another 55 gigawatts of nuclear under construction today, all large light water reactors. Of course, these are very complex, large scale projects. They're typically 1 gigawatt plus per reactor. And then we have this whole new world of small modular and advanced reactors. That technology is actually not new. The technology has been operational since the 1960s, but really more on a demonstration scale in the national labs. And a couple of countries like Russia and China have a few of these reactors operational. But what's really attractive about these reactors, one is that they're smaller, so it represents less of a complex infrastructure project and more of a manufactured product that can be manufactured in factory and then brought to a site and installed. But also these technologies, many of them operate at higher temperatures than existing nuclear power plants, which make them pretty ideal for non-electric applications, in this case, hydrogen production. So we have a couple, 3 different pathways here, and I will kind of rate them on technology readiness, a scale. If you look at low temperature electrolysis, both existing nuclear reactors and advanced reactors can be paired with that process. Right, all it involves is hooking up an electrolyzer to either the grid, of course, but you can also do this behind the meter directly to an interconnection from a nuclear power plant. So that ensures that your hydrogen is being produced with zero carbon nuclear energy. In addition, With high temperature electrolysis, that's using solid oxide electrolysis cells or solid oxide fuel cells, depending on kind of what part of the process you're talking about. And both existing reactors and advanced reactors can be paired with this more efficient electrolysis process. The interesting thing is with existing plants, even though they don't operate at as high temperatures, you can simply make some fairly easy modifications to them, like add an additional heat exchanger, for example, to increase the temperature. And then you get this, this more efficient process. And this process has been demonstrated, with some projects, for example, at Idaho National Labs, to be potentially 45% more efficient than low temperature electrolysis. So if that can work out at scale, that's a significant savings, right? Because about 75% of the cost of an electrolyzer is really the need for electricity. So if you can use some of the heat that is produced at nuclear power plants currently, which is wasted, it's literally called waste heat, then it can work into this process. And then, of course, with advanced reactors, they naturally operate at higher temperatures, so they are already designed to be able to be paired with higher temperature electrolysis processes. And then the last potential process that it can be used is thermochemical. So that is water splitting at very, very high temperatures, about 850 degrees Celsius or higher. And for that, you need a very specific type of reactor, a very high temperature gas reactor. There is a pilot to do that in Japan. There is some work being done in Canada and a few other countries on this process. It is a much lower technology readiness level, but it does present a future pathway. So it'll be interesting to see if it kind of makes it out of lab scale and into commercial readiness today. So these are the processes, but to kind of summarize, how nuclear technology and hydrogen applications work together. So, on the basic level, nuclear is zero emissions. So it represents a source of clean energy, both electricity and steam. Which is one of the differentiators that it has, right? That it can produce steam, not just electricity, and therefore they can be paired with these more high efficient hydrogen production processes. It's also firm and reliable with very high capacity factors. So in the US, for example, we have really the best operating track record as far as reliability. And our nuclear power plants in the US average a capacity factor of 92%. So these plants are, highly efficient, and they work around the clock. They're not susceptible to weather effects. And in fact, even with some of the extreme temperatures that we've been seeing lately, nuclear power plants have been able to work through that. So they can really produce hydrogen 24/7 if that is needed. Also, because they are so large scale and have these high capacity factors, they can produce huge amounts of hydrogen with actually a fairly small percentage of the electricity or heat being siphoned off the plant. So that addresses some of the issues and, kind of scaling up the market, the hydrogen market, by needing a low carbon source that can produce significant amounts of hydrogen really today or in the next couple of years, and nuclear can do that. Also importantly is that nuclear is super energy dense. So, I've had some maps here that I'm not going to put on into the slides, but you can see, a little dot of where there's a nuclear reactor, being able to produce as much hydrogen as other sources that, cover, the size of, half of the United States. It's a really energy dense source, and that can also contribute to its ability to provide large scales of hydrogen. And then I was talking about these advanced reactors, these small modular reactors. Sometimes we use these terms kind of interchangeably. Small modular reactors just refer to its size, the size of the modularity. Advanced often means that they can operate at higher temperatures, so slightly different technology. But they have these unique capabilities. I already mentioned the modular construction and the temperatures. But they also, because they type of technology that's being used, they're sort of inherently safe. So already the regulator, the Nuclear Regulatory Commission, which licenses these plants, has determined that the evacuation zone that's normally required can be limited to the size of the actual site. Which is a game changer for nuclear about as far as where it can be located. Because traditionally with large plants, they've had to be located away from population centers, which also often means away from industrial centers. Now with these small modular reactors, they can actually be co-located at industrial sites with industries that are looking to utilize hydrogen, and that addresses the transportation issue. You remember that both Shay and Beth talked about the need to transport hydrogen, kind of the difficulties you have in needing to construct pipelines or use existing pipelines or convert to ammonia and then crack back into hydrogen. So if you can put this reliable zero carbon energy source, a small modular reactor at an industrial site, you eliminate the transportation issue. Or even if you can't put it at the site itself, if you can put it in the same geographic region, it really, really does reduce the transportation costs, which is key in meeting all of these policy goals. So you can ask, is this nuclear hydrogen, is this kind of an idea? What is happening? What's the reality of it? So we actually at Pillsbury, we maintain a hydrogen map that tracks all of the operating and kind of we deem to be real hydrogen projects, ones that look to be at a sort of an advanced stage of development. And there are a number of nuclear hydrogen projects actually today. So right here in the United States, we've got 3 different pilot projects. One is actually operational. It's at a 9 Mile Point nuclear site that is owned by Constellation Energy in upstate New York, and it's actually producing hydrogen today. It is a demo. Constellation is actually incorporated hydrogen, and Constellation, for those of you not familiar, is the biggest generator of nuclear energy in the United States, and they're using this project as a way to demonstrate nuclear hydrogen production to then incorporate hydrogen into their strategy across their nuclear fleet. And they've actually also announced recently, after the selection for one of the hydrogen hubs, that they're going to be producing hydrogen at a large scale at another one of their nuclear power plants in the Midwest. There are also projects at Energy Harbor in Ohio. There were some efforts at APS in Arizona that they were looking at, and also the Xcel Energy in Minnesota. You have European projects. Électricité de France is planning to produce hydrogen both in France, in the UK. You have existing hydrogen production in other countries, for example, in Brazil, that is now being captured, and in other countries like Japan. My apologies, I don't know what's going on with my voice. I was at the Marine Corps Marathon cheering on my friends, and maybe cheered too loudly, so my my voice is it's kind of struggling this morning. But wanted to get into some of the incentives, and you already heard a little bit about the incentives, actually a lot, I think, from the other speakers, but I wanted to focus a little bit on where nuclear plays into this. So it's important to recognize that nuclear hydrogen production has actually been incorporated into most of the significant hydrogen incentive packages. So in the US, has been clearly incorporated into the IIJA, which stated that at least one of the regional hydrogen hubs has to be based on nuclear. And nuclear is also included based on the life cycle emissions in the highest tier of the PTC available, as she had mentioned. The DOE made its big announcement at H2 Hubs on October 13th, with 7 hubs, and 3 of those actually are producing hydrogen from nuclear, among other sources. To weigh in the 45V issue, of course, I think we can have a separate webinar to kind of discuss that. The nuclear industry, and the nuclear industry is, by the way, not alone. As an example, Treasury got about 200 comments with respect to 45V, as well as 45Z for clean fuels. And in general, industry is strongly challenging the additionality requirement, because it's being sort of uniquely suggested to be imposed on the hydrogen industry versus other industries and that are sort of in the same level. And the hydrogen industry is, it's very much burgeoning. And I mean, it's so young. And to impose this requirement is not was not only not included in the IRA and envisioned by Congress, but it also seeks to undercut this very young hydrogen market, where I can tell you that every single one of the clients that I'm working with on hydrogen projects, whether nuclear, renewables, or natural gas with CCUS, are relying on this credit in order to proceed. And I think every single one of them, if they're not eligible for the credit, those projects will be dead, which is really not great for the growth of the hydrogen market. For the nuclear industry in particular, a lot of it does not even make sense, because, as I mentioned, most of the nuclear hydrogen projects proposed are behind the meter. So they're not even using grid electricity. So we know the electricity is coming from the zero carbon source. And about the worries of diverting the energy and that being replaced by fossil fuels, because of this energy density of nuclear, nuclear can actually make significant amounts of hydrogen without any significant diversion of electricity. So that's really not consideration for nuclear. And as mentioned, Congress clearly envisioned nuclear hydrogen production to be included in both the IRA and the IIJA. So going against that and somehow precluding existing nuclear power plants from eligibility for the credit would be, in contravention of the intent of Congress. Wanted to just very quickly mention that, the U.S. is not alone in including nuclear hydrogen production in its incentives. So Canada has similarly done the same, specifically including production of hydrogen from both existing nuclear power plants as well as future small modular reactors, and providing clean investment tax credit for hydrogen production, for which nuclear would also be eligible, in addition to actually putting in specific nuclear production incentives. The UK very similarly has included nuclear hydrogen production in their strategy. And the EU is complicated, as Shay mentioned, and I'm not going to spend too much time on this, because this could take a 2-hour discussion. I have about 10 slides that I could present on what's going on in the EU, because it's become so complicated. But as Beth mentioned, and as Shay mentioned as well, the EU has agreed to impose this additionality requirement on renewable fuels of non-biological origin. It doesn't kick in until 2028. But interestingly, the EU has actually excluded countries that have a decarbonized energy mix, which includes countries like France that rely, 70+% on nuclear electricity, and therefore don't have this concern about fossil fuels replacing electricity siphoned off to hydrogen production. But the EU is in this very weird paradigm where they've divided hydrogen production into renewable hydrogen and then low carbon hydrogen, which is supposed to be nuclear and natural gas. And I'm someone who is just really against trying to divide hydrogen production by production sources. To me, it really makes sense to be based on greenhouse gas emissions, because that's ultimately the purpose here. It's not to kind of politically divide hydrogen production sources. So that's one of the issues, is that nuclear hydrogen production is generally basically exempt in a lot of these countries from these requirements, but it's also not included when it comes to all the incentives and the targets. So that's it. I've run out of voice and I've run out of time, and now, happy to answer any questions going forward. Thanks.
That's great, Alina. It's obviously another exciting kind of way to produce hydrogen, and one that shows a lot of promise. Pete, I mean, we've heard from a lot of the producers or folks on the producer side in terms of technology. We'd love to hear from you how all this looks from the NGO perspective.
Yeah, thanks very much, everyone, for speaking already. I'm really excited to offer the environmental perspective. I'm an advocate at the Natural Resources Defense Council, and I lead our work on hydrogen at the regional and state level, as well as helping with our federal advocacy as well. So yeah, I'm going to talk about hydrogen production mostly, as that is the theme of the day, obviously, but I also have a few things to add at the end around hydrogen emissions, so leakage of hydrogen itself, and around where hydrogen should be used, because I think that's really a pertinent question when you're thinking about how to make the hydrogen, is how you're going to use it as well. So to think about fossil fueled hydrogen production to start with, this is what kind of Rick described in its various colors and forms. Fossil fuel pathways, really from an environmental perspective, should be minimized. There's a few sources of greenhouse gas emissions throughout the whole life cycle chain of supply chain of fossil fueled hydrogen, that include methane leaks from upstream gas production, uncaptured CO2, or just all the CO2 that's produced if it's gray hydrogen, but uncaptured if it's this blue hydrogen. And then also we need to be sure about like the permanence of sequestration, if it's being used for something like enhanced oil recovery, or wherever the CO2 is going, we've got to make sure it's locked away and not allowed to enter the atmosphere. And there's also local pollution impacts from things like SMR. It produces other non-greenhouse gas pollutants that are really harmful for local communities who live close to these installations. So yeah, even in the best case, blue hydrogen is not going to be zero greenhouse gas emissions. You're not going to capture all the carbon dioxide, and there's always going to be some upstream methane leakage, which has to be monitored and controlled, and we want to avoid prolonging the lifetime of these fossil fuel infrastructure. Moving on then to biogenic production, which hasn't been mentioned yet, so I just added a slide on this because I wanted to make sure it was covered. You can do the same process as in gray and blue hydrogen, the steam methane reformation, or SMR, but with biogas produced from biogenic sources. This sounds like it might be a great idea, but there's some serious concerns around this as well. If it's produced from dairy manure in particular, sometimes referred to as moo hydrogen, this can be really bad in terms of incentivizing dairy producers to make as much methane as possible, so to treat their manure in a way that creates a lot more methane than is necessary, and then crediting themselves for having avoided venting that methane to the atmosphere, and giving themselves a huge negative carbon intensity based on the avoided venting of that methane. That's not honest carbon accounting, and we really want to move away from that if possible. It's much better to minimize generation of methane in general, and then step 2, use any of that methane that is created unavoidably to as methane itself. It can be used in a variety of uses where we can't use methane, and you don't have the energy conversion losses of transforming it to hydrogen. There's also gasification or pyrolysis of biomass. We heard about pyrolysis of methane. You can do the same kind of thing where you heat up biomass or biogas in low or zero oxygen environment. And like the pyrolysis of methane, this is like pretty nascent technology. It's been demonstrated at a small scale, but we need to understand better the environmental impacts of like the byproducts. CO2 is often created, but if it's biogenic CO2, that could be okay. However, there's also ash, tar, PAHs, particulate matter, and other pollutants that we think will be produced depending on the source of the biomass and the particulars of the process. And just in general, for all biogenic pathways, we have to make sure that we're only considering using sustainable waste biomass, and we don't recreate the issues that we already have with bioethanol, any kind of biofuels we're growing crops for specifically, there's always going to be like land use impacts from that can be really detrimental to the climate. Moving on to, most of my slides are going to be about electrolytic hydrogen production, so the green and pink side of things. Electrolytic hydrogen production is extremely energy intensive. So it's the basics on these first two bullets, but yeah, the key point I want to drive home with this slide is that just to achieve the 10 million metric tons of clean hydrogen that the DOE is targeting by 2030, you need 500 terawatt hours of clean electrons. And that's more than the entire energy demand of the state of Texas. So that's a lot of electricity we're talking about. And we need to make sure we have rigorous accounting mechanisms and guardrails in place around sourcing of that electricity in order to make sure that we don't end up using fossil fuels. You've already seen this in a variety of charts today, but just want to emphasize that the electrolysis is the only technology really capable of unlocking this really, really high credit at below 0.5 kilogram of CO2 per kilogram, more than 95% reduction from the status quo gray hydrogen, and getting that $3 per kilogram. But it's really important that we're really rigorous with the accounting system and framework for how to calculate your carbon intensity to make sure that the things getting that incredibly lucrative subsidy are truly clean. So we need really strong guidelines around the 45p tax credit that's been discussed. Even a small share of fossil fueled electricity powering electrolysis results in huge emissions that would blow past the threshold you're supposed to meet to get this tax credit. This is just a quick chart that demonstrates this. This tiny bar on the right here is the threshold to qualify for the credit. On the left, we've got the status quo 10 kilograms per kilogram from steam methane reformation without carbon capture. If you use the average grid in the US today, electrolysis is so energy intensive, it's twice as dirty as the status quo hydrogen if you use the average grid in the US. And if you use coal electricity, you're up even higher, 90 times the threshold to qualify for the credit. And so we really want to avoid any kind of accounting mechanism that might inadvertently allow even small amounts of average grid electricity or fossil fueled electricity into the mix. Yeah, there's hundreds of millions of tons of potential emissions at stake here over the lifetime of this credit. It's an uncapped credit, so we need to really make sure that we're rigorous. And the only rigorous form of accounting to do this is the 3 pillars. And yeah, as I'm about to go into pillar by pillar, and as Beth teed me up nicely earlier, that yeah, these are the system of safeguards that we think can ensure squeaky clean power for this process that is so energy intensive. So the first one is new clean supply, also referred to as additionality. This means that the hydrogen project just has to be powered by clean energy that's not currently supplying a load on the grid. The alternative is that a hydrogen project can just plug into the grid or to an existing resource that's serving the grid and use that power, divert that power, and in effect cause the ramp up of whatever is the marginal generator on the grid. And that is likely going to be fossil fuels most of the time. The net result is that you've actually powered effectively your hydrogen production with fossil fuels, and that means that emissions are going to be very high, way above the threshold. So if you do allow existing resources to qualify for the tax credit, you're going to be kind of lying about whether you're meeting this really high bar of $3 a kilogram. And actually, even in a state like California, which I've highlighted here, where there is an RPS that you'd think would alleviate these concerns, you still see these really high carbon intensities effectively when you include the indirect emissions impacts on the grid. Shouldn't be too hard to implement. We just need to make sure that hydrogen developers either build their own dedicated renewables, of course, that's like the easy option to do this, or enter a power purchase agreement with new clean energy projects. The EU have done this by using a 36-month kind of vintage rule, and something similar to that would work well here. The second pillar is hourly matching, the temporal matching side of things. This means that they have to operate during the same hours. It's pretty simple. Renewables are variable. We want to encourage electrolyzers only run when renewables are actually available. We don't want to credit them for running when there's no sun shining or wind blowing and they're claiming to use those resources. Annual matching is the alternative, and this would result in much higher emissions. This is just some data from MIT showing all the annual matching scenarios with much higher carbon intensities. I'm going to skip through this. And the third one is geographic deliverability. This is the simplest one. If it's not generated in the same area and deliverable, physically deliverable to your electrolyzer, then it shouldn't count. And we think that the e-grid regions, which are part of the EPA's kind of reliability work, are the most relevant kind of geographic regions to do this by, but there could be some special exceptions. If specific transmission is built out beyond these regions, then there's an argument that that should be included as well. Okay, so we've heard a little bit that maybe these three pillars might be too constraining on industry, and it will stifle this nascent clean hydrogen industry. Well, we have, thankfully, a really great real-world example from the EU who've put into the RFNBO delegated acts these rules to be phased in over the course of the next few years. And since those rules were announced, you can see on in the right-hand pillar, the pipeline of projects have actually increased significantly since before the three pillars were announced to be included in that. So we've seen the industry respond really positively to the regulatory stability provided by this framework, and now they know that what it's going to be. They're able to get planning and building these projects. And this pipeline growing is a great example that these aren't too much for the industry to handle. We should build out the industry in a clean way from the start. In the US, we have great modeling to show the same thing. This just compares limited requirements and the three-pillar requirements on the 45V tax credit, showing really similar build-out of electrolyzers in both cases, but obviously much, much better outcome on the emissions front with the three pillars. There's also other non-emissions impacts, things like costs onto energy ratepayers. If we don't have these three pillars to account for energy sourcing, drive up costs for consumers and really unfairly push the costs onto other people who aren't responsible for this increase in load, whereas the three pillars ensure that the people who are adding load to the grid, that the hydrogen producers are ensuring that the generation is added in the right place, at the right time to meet that load. Without this, the hydrogen industry faces a real credibility issue, and I would anticipate a lot more public opposition to the build out of this industry. And finally, as Beth said, flexible operation is key, and the three pillars incentivize that, which will encourage innovation and US manufacturing as opposed to importing a lot of inflexible electrolyzers manufactured in China, likely. I don't have much time left, so really, really quickly want to just highlight one issue beyond production, which is hydrogen leakage or hydrogen emissions. Hydrogen itself is an indirect greenhouse gas. There's tons of research now showing this. It extends the life of methane in the atmosphere, and that net result is a warming effect that is 30 to 40 times more potent than CO2 on a per kilogram basis on a 20-year time frame. This means that if leakage is high, and we don't currently know how high it is, but if leakage is high, it can completely undermine some or all of the climate benefit of using hydrogen to replace fossil fuels. So what we're pushing for is for leakage monitoring and avoidance, basically, to ensure the actual climate benefits of hydrogen. We need to develop the sensing technology and the protocols to do this. Currently, the industry doesn't monitor leakage well. They obviously monitors it for safety reasons, but for the climate, we need to monitor really small leaks as well. This is just a figure from a recent paper that shows quite how divergent the estimates are for hydrogen leakage across the value chain. You can see it ranges anywhere from less than 1 to 20%. If it's up in the upper range of this is completely annihilating any climate benefit from using hydrogen. So we really need to get better at recording this data, and and then including the climate impacts of hydrogen in our life cycle assessments, because right now we just don't know what the impacts are here because we have no idea what scale of leakage we're facing. Then I was going to talk about hydrogen applications, but looking at the time, I think I'd better skip these slides and just say very briefly, you've got to only use it where it makes sense in those hard to electrify sectors and not waste it on things like building electrification and load and passenger transport, things like that. And just also a note that combustion of hydrogen produces NOx, and we've got a control for that as well. So with that, I will leave you and invite any questions. Thanks so much.
Amazing, man. Thank you for fitting all that into the last sector. We didn't leave you with a ton of time, so appreciate that. Well, look, Sarah, my colleagues here have been doing an excellent job of answering the Q&A as we've gone. They've been really good about answering these questions. So we don't actually have any outstanding questions that are left in the Q&A box, and we're right at 1:30. So do you want us to kind of wrap it up now? How would you like to proceed?
I think you're welcome to start wrapping it up if you'd like to. If there's any like last minute kind of question you want to ask everybody, but that's up to you. I think we're ready to start wrapping it up.
Yeah, that sounds good. Well, I guess, let me see if I can. Okay, let me throw out there one last question for folks. So I guess a generic question to maybe wrap things up is like, what's your view as kind of what the biggest hurdle is to hydrogen commercialization? And then I'd also ask you to posit a solution to that hurdle, just so we can think about that a little bit on the way out. Okay, see you, Rick. But let me throw that out there. Rick, are you sticking up?
Yeah, I was just gonna take a shot at answering.
Oh, sorry, I thought you were giving a goodbye wave. So okay, Rick, why don't you kick us off then, since you volunteered here?
Yeah, so I think it's just math, right? Everybody's got a calculator or Microsoft Excel, and when you start penciling this out, it's just, even if we can get to $1, right? So everybody's all excited about $1 a kilogram, but the first question is $1 a kilogram where and for what use? And what people don't appreciate, and look, I'm a hydrogen evangelist, right? I really do believe in this, and I believe it's a solution for 10 to 20% of mankind's clean energy needs long-term, hard to decarbonize industries. But here in the US, if you use the figure $8 a million BTU for natural gas, you're going to excite absolutely no one. And $1 a kilogram on an energy basis is comparable. So what do I see the biggest challenge on adoption is just simply cost and people's ability and willingness to pay more for clean energy as opposed to, the gray discount they've been getting all these years. So that's, sort of my 2 cents on top of the $1.
Yeah, and I would just add that I think clean energy build out is one of the biggest things we need to get better at. So resolving any kind of permitting and siting issues that are slowing us down, getting the amount of clean energy built that we need to, both for the grid, but also for hydrogen. We don't want to be cannibalizing our existing resources for this. We want to be building out as much new as we can for the grid and for hydrogen. So speeding that process up and deploying clean energy is going to be the key thing to rolling this out.
Sounds good. I'm back. Alina, do you want to take it over next?
Sorry, having trouble unmuting. Yeah, I would just add my 5 cents to the cost issue. I think the cost issue is really the biggest one. The numbers have to work, and to me, one of the biggest drivers here, other than things like lowering the cost of the electrolyzers and making them more efficient, is the transportation issue. I think the transportation issue, can triple, quadruple, quintuple the cost, depending on which study you look at. So to me, it's just optimizing, thinking about the geography, optimizing the resources you have. Where can the existing resources can be used? Where can you build out new ones, realistically, for the cost that's needed for the market. So instead of, approaching this in a political way, which oftentimes happens, you really have to approach it in a scientific and mathematical way.
Yeah, do you want me to jump in, Shay, real quick? So I think cost. There's great agreement on that, but also I think these rules need to be finalized in a way that is clear quickly. I think without certainty, it's going to drag actual projects getting into the ground. I think the quickness is more important than the perfection, I would say. And so getting a final rule that is sending the right signals so people know what to do, similar, as I said, to what Europe is doing, is going to be really important that that happens. And then, I think the other side is that to really focus on is demand side. A lot of these incentives are more on the production side, but I think you also have to think about incentives to kind of make folks think about changing over their stranded assets. Europe is doing some auctions around that this month for the first time, some pilot contract for difference kinds of solutions. I know DOE is thinking about this as well in the US, and I think that's going to be the emerging issue.
Great. Yeah. Well, thank you all for all your input. Yeah, and I think the challenge that you all mentioned that's really common to decarbonization of everything is that these things are expensive to implement, and there's essentially a zero green premium that people are willing to pay for everything. And so how are we going to decarbonize everything when there's very little consumer tolerance for paying extra for these things is the big challenge. It could be hydrogen, it could be sustainable aviation fuel, it could be kind of the transportation fuel markets more broadly, but it's a really big challenge that we have to figure out, and hopefully the IRS can kick us in the right direction with this guidance. But thank you all again to all of you for all your expertise. It's been a great conversation. I look forward to chatting with you all about these issues more as we continue to develop this market in the United States.
Yes, thank you so much to all of you for being here. My apologies, we went a little bit long today, so if you're still here, thank you so much for sticking around with us. Thank you to Shay for moderating, and thank you to Pete, Alina, Beth, and Rick for all of your wonderful comments. I think we'll have to do a part 2 sometime to get to all of the rest of this discussion. But we do have a very similar conference coming up on November 8th, Green Tech. Green Tech focuses on implementing green technology through the IRA to accelerate the energy transition and decarbonization. So there's going to be sessions talking about hydrogen and renewables. So if you're interested, you can go to greentechconference.org for a lot more discussions like this. And if you couldn't attend the full webinar today, if you joined late, you'll be able to watch the recording on our event webpage. It'll be up within a few business days, probably by the end of the week. We hope to see you all at future programming, which you can find at eli.org. So thank you all and have a wonderful rest of your Monday. Bye, everybody.